Now the next question, this is from the GATE question paper. This is asked in one of the GATE question papers. A power station consists of two synchronous generators A and B of ratings 250 MVA, 500 MVA with inertia 1.6 per unit, 1 per unit on their own base MVA ratings. On their own base MVA rating. The equivalent per unit inertia constant for the system on 100 MVA common base is. So we have two generating stations here. First, synchronous generator A. So how H and S are related? You are given the inertia constant there, 1 per unit. But formula wise, H and S are directly related. So S is 250, here 1.6. With respect to 100, you don't know what is HA. So we have to calculate this one. HA is 1.6 into 100 by 250. So H and S. So you know this basic formula now. M is SH by pi F. So how H and S are related? Inversely related. So initially given 250 is S value and it is 1.6. With respect to 100, you find out what is the value. 1.6 into 250 is HA into 100. You calculate what is the value of HA here. You get it as 4 per unit. Now you check the synchronous generator B. What about now? 1 per unit, 500 per unit, MVA. With respect to 100, we have to calculate. So 1 into 500 is HB into 100. So calculate what is HB, you get 5 per unit. What is H equivalent? It is HA plus HB. 4 plus 5, it is 9 per unit. How much you get? It is 9 per unit. So these are the questions based on coherent swinging and non-coherent swinging of synchronous machines. Now we discuss the next topic. that is equal area criterion method. Equal area criterion method. Now we analyze the solution of swing equation for two machine system using equal area criterion method. But both synchronous machines have equal size, therefore equal moment of inertia, therefore equal frequency of rotor oscillations, therefore both synchronous machines swing together. Now you consider the swing equation now. M d square delta by dt square is Pa. So how much Pa is Ps minus Pe. So mechanical input minus electrical output. So this is how you begin our analysis here. So now in the next step you mention d square delta by dt square. How much you get? 1 by m times Pa. Are you right? 1 by m times Ps minus P. This is how you write d square delta by dt square here. Now this left hand side term can also, now what you do is left hand side term and right hand side term you multiply with 2 d delta by dt. So both left hand side and right hand side you multiply by this terms here. So here how much you get? 2 by m d delta by dt Pa. Now how to represent this left hand side term? Now it is the derivative of d delta by dt whole square. So what you get on differentiating this 2 times d delta by dt, then d square delta by dt square. Now further you have to integrate. So on integrating what you will get now? D delta by dt whole square is 2 by m integral Pa d delta by dt here. So how much you get? 2 by n times integral of Pa into d delta. 2 by m times integral of Pa into d delta. Now you know that initially what is the load angle? Initially the load angle is 0. That initially what is the load angle? Delta naught. What about the delta naught constant? And whenever you differentiate a constant you get it as 0. So now you mention like this: before any disturbance occurs, before any disturbance occurs, what about delta? Same as delta naught is constant. In such case, what will be d delta by dt? 0. As it is 0, what about the equation 1 now? We can write 2 by m integral Pa d delta is 0. Now when this can be satisfied? 2 by m cannot be 0. Therefore, how you satisfy this equation? Integral Pa d delta is 0. Integral Pa d delta is 0. How to write what is Pa now? We will check now. So for that, you consider the power angle curve a part of that. You know that mechanical input PS is constant. Already we have assumed that the mechanical input PS is a constant. And what about this one? It is the variation of PE here. Now observe now, for this region, what about this region now? Say this region area is A1, this region area is A2. So now you consider the area A1. In this area A1, what you will have? Electrical output is less than the mechanical input. Electrical output is less than the mechanical input. So PE is less than PS. Then how to write this equation further? It is mechanical input minus electrical output is 0. Now what about PA now? Formula wise, PS minus PE. PS greater than this one, so PA is positive. What is the meaning of PA positive? PA positive means rotor accelerates. What happens when the rotor accelerates? Omega will be greater than omega s. And further, the kinetic energy is stored by the rotor. Now you consider the area A2 now. Check in this area A2. Electrical output is greater than this mechanical input PS. So electrical output greater than mechanical input. So what will be the acceleration power? It is negative. What happens when PA is negative? When PA is negative, rotor decelerates. That is omega less than omega s. Then what about kinetic energy? Whatever kinetic energy is stored by the rotor earlier is restored back to the system. So kinetic energy is restored to the system. Now, when these two areas are equal, what happens? PA positive, PA negative. When these two are equal in magnitude, the net area enclosed is 0. The net area enclosed is 0 and this relation is satisfied. So in order to satisfy this relation, areas A1 and A2 must be equal. Hence this technique got the name equal area criterion method. I repeat, how you satisfy that equation? Area 1, area 2 must be equal. Then only you can satisfy the equation. Therefore we name it as equal area criterion method. So wherein it is satisfied, areas A1, A2 must be equal. So hence you name it as the equal area criterion method. Hence you name it as what? The equal area criterion method. So this is regarding the equal area criterion method. So now we check what is the statement of equal area criterion method. You can observe here the net area enclosed by synchronous machine between the two successive swing points, that is during the first swing. That is during the first swing is 0. The net area enclosed by synchronous machine during the first swing or between two successive swing points is 0. That is, the area of acceleration A1 must be equal to the area during deceleration, that is during the first swing. So that is the statement of equal area criterion method. So what is the statement now? Area enclosed by the synchronous machine between the two successive swing points that is during the first swing is 0. That is during first swing is 0. Or you say the area of area enclosed during acceleration of rotor equal to area enclosed during the deceleration of rotor. This is what you name it as the statement of swing equation. Not only this, swing equation also gives the information regarding angle made by the rotor at the time the fault is cleared, which you name it as critical clearing angle delta C. So what else you can find using using this equal area criterion method? It also provides angle of the rotor at the instant fault is cleared, by the circuit breakers and relays. And what you call that angle as critical clearing angle delta C. You name it as critical clearing angle delta C. So this is the analysis of equal area criterion method. Now we have the assumptions of equal area criterion method. That is, when you say stable operating point or when you say swinging operating point, and how the delta change is influenced by. So first one is stable point. So what does this stable point equal to 0? PA equal to 0 and omega equal to omega S. And what about the swinging point? PA not equal to 0 or omega not equal to omega S. Further, the change in the rotor angle delta is influenced by moment of inertia. So these are the three assumptions of equal area criterion method. And now we discuss the applications of equal area criterion method. Now we write the applications of equal area criterion method. Now the first application, you consider a synchronous generator. So what is the input to synchronous generator? Mechanical input. What is the output of synchronous motor? Electrical output. So we now analyze sudden increase in mechanical input to synchronous generator. So first one is sudden increase in mechanical input to a synchronous generator. So we represent the synchronous generator here along with the reactance connected to infinite bus bar. What about this angle? E8 angle delta, bus bar V8 angle 0. And what is the mechanical input initially? Say it as PE1. Say the electrical output is PE1. Now say the mechanical input is increased. Increased to where? PS2. Accordingly, the electrical output is increased to PE2. Accordingly, increase the electrical output to PE2. So this is what we analyze here. Now we check how the operating point shifts on the power angle curve. So this PE versus delta here. So initially, say the operating point is A. For what is the mechanical input? It is PS1. And at the operating point A, what is the load angle? It is delta naught. So what about that load angle? It is delta naught. Now first we analyze at the operating point A. So what about the acceleration power PA? PS1 minus PE1. How to write this PE1? PM1 sine delta naught. Both are equal, so PA equal to 0. And what we write when PA is equal to 0? Rotor neither accelerates nor decelerates. Rotor neither accelerates nor decelerates. So what will be the value of omega? Equal to omega s. And which point it refers to? Stable point. Because we require both PA0 and omega is equal to omega s. Now you say mechanical input is increased. To which value it is increased? Say to some value PS2. Say this operating point is B. Say corresponding value of this delta is, you indicate by delta 1. And now we check the transition from A to B. So what is PA now? Mechanical input is increased. But what about the electrical output in this duration? This is the electrical output. Here mechanical input. You can observe electrical output is less than mechanical input. So electrical output less than mechanical input. What about this value of PA now? It is positive. Or else how you can write this one? PM2 sine delta. And what is the range of delta between delta naught and delta 1? As PA is positive, what about rotor now? Rotor accelerates. What about omega greater than omega s? And what about this operating point? It is a swinging point. Then what about the value of delta now? Increases. Why it increases? You know, for a synchronous generator, whenever rotor accelerates, delta increases. You come across these points in electrical machines, synchronous generators. When a synchronous generator accelerates and omega greater than omega s, delta increases. So we mentioned there, delta increases due to acceleration. And now you reach the point B now. So what about PA? PS2 minus PE2. Now what is PE2? PM2 sine delta 1. How much it is? 0. When this PA is 0, what about rotor now? Rotor neither accelerates nor decelerates. Then what is the value of omega now? Always you write omegas by comparing with the last step. In the last step, rotor accelerates. Omega greater than omega s. Now rotor neither accelerates nor decelerates. What about omega? Equal to omega maximum. So last step rotor accelerates. Now rotor neither accelerates nor decelerates means rotor stopped accelerating. When the rotor stops accelerating, when the maximum speed is obtained. When the maximum speed is obtained. I repeat, in the last step rotor accelerates. Now when the rotor stops accelerating, when the maximum speed omega max is obtained. Now again it is a swinging point. Again it refers to swinging point. What about delta now? Further increases. Because even though you got PH0, the delta continues to increase. Because right from the point A, delta is increasing. Now at the point B you got PH0. As you got PH0, delta will not stop. It will further increase. See, when you are going on a bike, you apply the brakes. Will it stop at that same instant? Say maybe after 1 feet or 2 feet. Same thing applies here. You got PH0, but delta will increase, continues to increase. So it continues to increase further. How long? You don't know. Assume that as some point is C. And say this is the maximum value of delta. Say that is the maximum value of delta there. So delta increases. Why? It is due to moment of inertia. This is the third assumption we have written in the assumptions of equal area criterion method. Increase in delta is due to, or you say the change in the rotor angle delta is influenced by moment of inertia. The change in rotor angle delta is influenced by moment of inertia. And now you check from B to C. So what about PA? PS2 minus PE2. So PS2 minus PM2 sine delta. What will be this delta now? Between delta 1 and delta max. What about the difference now? Electrical output greater than mechanical input. Electrical output greater than mechanical input. So what is the difference? Negative. If PA negative, what about the rotor now? Decelerates. What about the rotor? Decelerates. So if the rotor decelerates, what about omega? Less than omega max. But still it is greater than omega s. So again it is a swinging point. Then what about delta? And due to deceleration, delta will not decrease, please, because you are having omega still greater than omega s. So what we mentioned, delta increases in spite of deceleration because omega greater than omega s. Delta increases in spite of deceleration because omega greater than omega s. Now you check at the point C now. What is PA? PS2 minus PE2. What is PE2? PM2 sine delta max. What will be this difference now? At this point, electrical output greater than mechanical input. Electrical output greater than mechanical input. So PA is negative. PA negative means what about rotor now? Rotor is decelerates. Then what about omega now? Finally, it is equal to omega s. So how long it can decelerate? Till that omega is equal to omega s. So you have reached the point C, omega equal to omega s. But PA is not 0. You know, for stable point, not only omega must be omega s, but PA must be 0. So what does it indicate now? It indicates the still a swinging point. What about delta now? Now decreases. Why? Because due to decelerations. So delta decreases due to deceleration. And now you come back in the reverse direction now. So at delta max, what is omega? This omega s. So you have traveled from A to C. Now check the reverse direction. Now you come back from C to B. So what is PA? PS2 minus PE2. So what is PE2? PM2 sine delta. And what is the range of delta now? Between delta 1 and delta max. What about the difference now? Negative. As the difference is negative, what about the rotor? Decelerates. What about the rotor? Decelerates. So what you write omega? Always you write omega by comparing with the last step. In the last step, omega is equal to omega s. Decelerating means now omega is less than omega s. And what does this point refers to? This point refers to swinging point, and due to deceleration, delta further decreases. Delta further decreases due to deceleration. And now you check the point B now. And what about PA? PS2 minus PE2. What about PE2 now? Pm to sine delta 1. What about this difference now? At the point B, electrical output same as mechanical input. Electrical output same as mechanical input. So what about the difference? 0. Then what about rotor? Neither accelerates nor decelerates. Neither accelerates nor decelerates. Then what should be the omega value now? You compare with last step and write what is omega. In the last step, rotor decelerates. Now rotor stopped decelerating. So when rotor stops decelerating, when minimum speed is obtained. When the rotor stops decelerating, when minimum speed is obtained. So what does it refers to now? This refers to swinging point. And why again delta continues to decrease? You have rotor neither accelerating nor decelerating. You got PA 0. So in spite of PA 0, why the rotor decelerates, delta decreases? Due to moment of inertia. Always to check at the in-between points B, always we have moment of inertia. So due to moment of inertia, the delta will decrease. So delta is decreasing from C to B. Even if you get pH 0, delta continues to decrease. Even though you get the point B, delta continues to decrease due to moment of inertia. So you apply brakes on a motorbike. You won't stop at the same instant, say after 1 feet or 2 feet. Same concept here also. Delta decreasing from C to B. Now delta continues to decrease due to moment of inertia. Due to moment of inertia. Now we mention now at this it is omega s. Now you got omega minimum. This from where to where? This from C to A. What about from B to A now? What about PA now? PS2 minus PA2. So how to mention this one? PS2 minus PM2 sine delta. What is the range of delta between delta naught and delta 1? So what about this difference now? You check now this difference. What about this difference is negative? You can check here. This is the electrical output much lesser than mechanical input. Electrical output less than this mechanical input. So PA is negative. PA negative means what about rotor now? Sir, it is positive. Mechanical input greater than electrical output. PA positive means the rotor accelerates. So what happens if rotor accelerates? Omega will be greater than omega mean, but still it is less than omega s. But still less than omega s. And what does this refers to? This refers to swinging point. And why delta continues to decrease further in spite of acceleration? You can check this point. In spite of deceleration, delta increases because omega greater than omega s. Now delta decreases in spite of acceleration because omega less than omega s. So delta decreases in spite of acceleration. What is the reason? Omega less than omega s. So lastly you check at the point A. This point A you get same as the very first point. So this point A is very much same as the first point. So this is how you have, again at this point, omega equal to omega s. Now in this you have to find the area enclosed by these two here. These two areas we have to calculate. This A2, this A1. And when you say the system is critically stable, when these areas are exactly equal, you say now the system is critically stable. So with area A1 equal to A2, then you say the system is critically stable. So this is how you analyze the first application, the sudden increase in the mechanical input to a synchronous generator. Now we analyze the synchronous motor. For synchronous motor we have input is electrical, output is mechanical. So now we do the second application, sudden increase in mechanical output of synchronous motor. Sudden increase in the mechanical output of synchronous motor. That is our second application. And our second application is a mirror image of the first application only. Sudden increase in the mechanical output of synchronous motor. So electrical input PE1, mechanical output is PS1. Now say the electrical input how much? Electrical input will increase due to sudden increase in the mechanical output, this value will increase. And we can indicate for synchronous motor here. What about this angle? This you mention V at angle 0. At this point we have E at angle delta. So this is how you represent a synchronous motor notation here. The notation of synchronous motor. So again we have to analyze by drawing this power angle curve. So how to analyze by drawing this power angle curve? You represent delta and here it is P. So first to represent this power angle curve. On this power angle curve, so always the initial operating point you say it as A. And what about the corresponding load angle? Make it as delta naught. Corresponding load angle is delta naught. Now we have the mechanical output PS1. Now this mechanical output is increased to PS2. Say the corresponding operating point is B. And at this B, say the corresponding load angle is delta 1. Say the corresponding load angle is delta 1. So this analysis again we redo now. First to check the operating point A. At this point A, mechanical output same as electrical input. So what is PA? PS1 minus PE1. Both are equal, PH0. So what about rotor? Neither accelerates nor decelerates. So omega equal to omega s. Indicates stable point. Now you check from A to B. Now mechanical output is greater than the electrical input. Mechanical output greater than electrical input. So what about the difference now? It is negative. What about the difference? It is negative. If PA is negative, what about rotor? Decelerates. So omega less than omega s. Now for synchronous motor, whenever rotor decelerates, what about delta increases? For a synchronous motor, whenever rotor decelerates, delta increases. And now you reach the point B. What about PA? So every time you mention here, electrical input, mechanical output, PE1, PE2, so what will be this PE1? PM1 sine delta naught. Here difference 0. What about this one? PM2 sine delta minus PS2. This difference is negative. And what is the range of delta between delta naught and delta 1? Now check the point B now. At this point B, mechanical output same as electrical input. So electrical input minus mechanical output. So PM2 sine, there it is delta 1. What about the difference now? 0. So what happens to rotor? Neither accelerates nor decelerates. So what will be the value of omega now? In the last step, rotor is decelerating. Now rotor neither accelerates nor decelerates means rotor stops decelerating. In the last step, rotor decelerates. Now rotor stops decelerating. So when the rotor stops decelerating, when the minimum speed is obtained. When the minimum speed is obtained. And at the point B, even though you got pH 0, why delta increases? Due to moment of inertia. You don't know how long the delta increases. We assume that the delta increases up to point C, corresponding to the load angle delta max. So you are traveling from A to C now. Initially omega s, next to omega minimum. And now we check at the point B to C. So electrical input minus mechanical output. So how to represent these values now? PE2 is PM2 sine delta. What will be this difference now? This difference is positive. So when the difference is positive, what about the rotor now? That rotor accelerates. So what will be omega now? Always you write omegas comparing with last step. In the last step, omega is equal to omega min. From here, the rotor accelerating means greater than omega min, but still it is less than omega s. But still it is less than omega s. Again it is a swinging point. Then why delta increases? For a synchronous motor, due to acceleration, delta should decrease. But why the delta increases? Because omega is less than omega s. So delta increases in spite of acceleration. Delta increases in spite of acceleration because omega less than omega s. Delta increases in spite of acceleration because omega less than omega s. Now check it the lastly point C in forward direction. So PE2 minus PS2. You can check it the point C. Electrical input greater than mechanical output. So the difference is positive. Rotor accelerates. So last step, how much? Less than omega s. Now what will be the value of rotor now? You reach the point C. The maximum value of delta you get delta max. There we get omega equal to omega s. Again it is swinging point. And why the delta decreases now? You have synchronous motor. So it decreases due to acceleration. Delta decreases due to acceleration. So at this delta max, what is omega equal to omega s. Now we come back in the reverse direction and verify the evaluation. So let's see as it is omega equal to omega s. And now come back from C to B now. What about C to B? Electrical input minus mechanical output. You can check from C to B. We have the electrical input greater than mechanical output. So the difference is positive. So rotor accelerates. So last step omega equal to omega s. Now it will be greater than omega s. Again point decreases to acceleration. Delta is due to acceleration. Check it to be now check it the point B. Electrical input same as mechanical output. So PE2 minus PS2 difference is 0. So rotor neither accelerates nor decelerates. So what will be the value of omega now? In the last step, omega is greater than omega s. Or you say rotor accelerating. When the rotor stops accelerating, when the maximum speed is obtained. When the maximum speed is obtained. It is swinging point. Delta decreases due to moment of inertia. Decreases due to moment of inertia. So now you check from B to A. So what about B to A now? PE2 minus PS2. From B to A you can check. electrical input is less than mechanical output. So what about the difference? Negative. If difference is negative, rotor decelerates. What about omega now? You can compare here. Last step, omega is omega max. Now decelerating means less than omega max, but still it is greater than omega s. So due to deceleration, delta should increase. But why the delta decreases due to omega greater than omega s? So due to that, what happens? The delta decreases in spite of deceleration, because omega is greater than omega s. Omega is greater than omega s. Now finally, to analyze, you find the areas of these two regions. This is the area A1, this is the area A2. You shade these two regions. So what about this one? Area A1, this is the area A2. When both areas are equal, then you say the system is critically stable. So my request is you once again go through each and every step carefully. At the first go, it is difficult to analyze each point. But revise 1, 2, 3 times, then you can find this topic much easier. So you refer this topic 2, 3 times, then you find it much easier. Only the principles of synchronous machines and no other point further. Lastly, you compare two areas and decide when both are equal, the system is critically stable. Now you have 5 minutes break.